We interact with screens so seamlessly, we often treat computers as singular tools. But beneath the glass, a computer is a highly structured processing engine. To understand how this engine operates, we start with its fuel, data. In computer science, data is strictly defined as raw, unprocessed information. The engine's primary purpose is to take that raw material and process it, running the data through a systematic series of logical actions to sort, calculate, or manipulate it. Once those actions are complete, the system outputs the result, transforming the raw data into communicable, human-readable knowledge. This sequence is mapped out in the information processing cycle. The diagram shows 4 interconnected stages: input, process, store, and output. Every digital architecture executes this exact 4-step loop. Whether it's a massive server rack or a portable laptop, the fundamental workflow is identical. Human language and abstract concepts are useless at the execution level of this cycle. To see how these physical stages connect, we look at the native language of the machine. The entire architecture of a computer exists to translate abstract human intent into physical, binary execution. Let's trace that execution from the beginning. Imagine pressing the keys on a keyboard to input the decimal number 103. The hardware cannot read the mathematical concept of 103. At the physical boundary, it only recognizes the presence or the absence of electrical current. To bridge this gap, the system relies on the binary number system, or base 2. It represents those on and off electrical states simply as ones and zeros. This row of 7 slots demonstrates how binary translates data. Reading from right to left, each position represents a power of 2. 1, 2, 4, 8, 16, 32, and 64. To convert decimal 103 into binary, the system checks these values starting from the largest. Because 64 fits into 103, the 64 slot activates, registering as a 1 and leaving a remainder of 39. Since 32 fits into 39, that slot gets a 1. However, the next 2 values, 16 and 8, are larger than the remaining 7. Consequently, those slots register as zeros. Finally, a 4 fits into 7, leaving 3. A 2 fits into 3, leaving 1. After the final 1 slot is filled, we are left with the completed sequence, 1, 1, 0, 0, 1, 1, 1. Architecturally, each individual 1 or 0 is a bit. When grouped together into a sequence to represent a single character, it becomes a byte. Through binary conversion, human abstraction is stripped away. What remains is a physical data payload ready for transit through the hardware. That byte leaves the input device and enters the motherboard's network of communication channels. This physical pathway is the bus. It acts as the transit system that lets all the discrete electrical components on the board communicate. The bus carries the data directly to its first destination, random access memory. RAM serves as the system's main memory. It operates as a holding zone for both data and operating instructions that are waiting to be processed. Because RAM relies on physical chips, it has a rigid capacity limit. When we measure memory in megabytes or gigabytes, we are defining exactly how much data those chips can physically hold at once. This diagram illustrates the volatile nature of RAM. It requires a continuous flow of electricity to maintain its binary states. If the power drops, those 1s and 0s instantly vanish. Ultimately, RAM acts as a mandatory buffer, holding data in electrical suspension until the primary processor demands it. When called upon, the data moves out of RAM and directly into the architectural heart of the system, the central processing unit. The CPU is the execution engine of the computer. It is the specific location where all actual data processing takes place. This schematic breaks down the CPU's internal architecture. The control unit supervises general operations, acting as a director that pulls the required data straight from RAM. The control unit routes that data to the second zone, the arithmetic and logic unit, or ALU. This is where mathematical calculations and binary manipulations occur. The third region consists of the registers. These are small pockets of hyper-fast internal memory, used solely to hold data for the exact moment the ALU executes an operation. The central processing unit functions as a mechanical coordinator, rapidly cycling through rigid instructions to manipulate binary states. Once the CPU finishes processing the data, that new information exits the processor and arrives at a fork in the architectural pipeline. One path routes the data into mass storage, such as a hard drive. Unlike volatile RAM, mass storage is auxiliary and non-volatile. It retains your data permanently, even when the machine is powered down. The second path directs the newly processed data straight to the output unit. Output is the reverse of the input translation. It converts machine state ones and zeros back into a format that a human being can understand. That translation could mean mapping binary bytes into thousands of specific pixel colors on a display screen, or directing precise placements of ink on paper. With the output rendered or data safely stored, the cycle has closed. Raw input has been mechanically transformed into permanent, useful information. Despite its structural complexity, this physical architecture remains inert on its own. Without specific instructions, the CPU and its subregions have no impetus to move data. The system requires software, the computerized, programmed logic necessary to command and coordinate those physical components. This stack represents how that logic is layered. At the very top sits application software. These are programs like word processors and spreadsheets that represent your direct human intent. Directly beneath the applications is the foundational tier, system software, primarily the operating system. The operating system is the system's hardware manager. It controls the input and output devices and allocates physical memory to ensure everything runs smoothly. The OS acts as the system's air traffic controller. It takes the high-level requests from your applications and translates them into the low-level binary commands required by the CPU and the bus. The complete stack operates from the top down. Human intent drives the application relies on the operating system, which commands the hardware via binary code. Computing relies on this symbiosis. Hardware establishes the physical limits of execution, while software provides the coordinating logic to process information automatically.